This is a revision video on orbital equations. So, orbital equations. In the previous videos, we went through all the concepts that we are using in finding out the values or the equations for all these parameters. But the main one we use, the basic fundamental law that we use is the Newton's universal law of gravitation, which is the force between two masses is equal to mm, but is the multiplication of the mass times the universal gravitational constant divided by the square of the radius. So if we write it here, the force between two masses, that's a mass, that's a mass. So the force, so this mass will attract that mass, this mass will attract that mass, and the force is equal to g m over r squared. So this is m and this is small m. So this is the equation that we will be using to find the equations for most of these variables like orbital velocity, orbital period, and gravitational potential energy and escape velocity. So let's go through everything one by one a bit quickly because it's a revision video. So the first one is the Newton's law of universal gravitation. What Newton said was if we have two masses, m and m, there's a attractive force. So this mass will attract this one that this is attracting, and the force is equal to g m over r squared. So m and m are the masses of these two objects, and r is the distance between them. So this can be sun and earth, or this can be apple and orange. Any two masses will exert attractive forces on each other. So that's the Newton's law of universal gravitation. So now we are going to find out the gravitational field strength from this equation, that Newton's law of universal gravitation. So we have Earth here, and this is a center of Earth, and at different levels, different altitudes from the Earth's surface, the gravitational field strength is different. It's not constant, and it depends on how far that point is from the center of Earth. So we're going to use this equation, Newton's the second law, which is F is equal to mg, to find out what that acceleration is. So let's see this at the top point where we have got gr, which is at distance r from the center of the Earth. So what is that force acting on it, which is F is equal to m, the acceleration, so which means mgr. But we found out that the force between that mass and Earth can be given by g m over r squared. So from here we can find out what is gr. So gr is equal to, so m and m will cancel out, so we will get gm over r squared. So that's the equation for the gravitational field strength at distance r from the center of a planet. So that would help us to find the gravitational field strength for at any planet and planet surface, or we can find out the gravitational potential strength at a distance. So that would help us to solve lots of problems that is to do with the gravitational strength. So we have a planet with capital M mass, and there is an object that is at a distance r from the center of the planet with a mass m, small m. So this is in circular motion and this is in orbit. So that means there's a centripetal force acting towards the center of Earth from that mass. So that centripetal force is provided by the gravitational force which we found out before, which is equal to the g times mm over r squared. So what we are going to do is we're going to equate that centripetal force to the Newton's gravitational force and find what is the orbital velocity of this little m. So let's say this orbital velocity is v. So we will write the equations for the centripetal force is given by, because it's in circular motions, we can write it as m times v squared over r. V squared over r is the centripetal acceleration. This is from circular motion. And the gravitational force, Fg, is equal to gmm over r squared. So the centripetal force is provided by the gravitational force. So that means mv squared over r is equal to gmm over r squared. From here, we can find out that v squared is equal to gmmr. So, before we do that, we can cancel this m and this m. So v squared is equal to gm over r. So we can write v is equal to square root of gm over r. So to find the orbital period, we can use the same equations, which is f c is equal to fg, but we have already done that, so we derived an equation v squared is equal to gm over r. But we know so this is about the gravitational potential energy, which is the fifth one. So when we consider distances that are not that much from the Earth's surface, we know that the potential energy is mgh. Mgh is the work done by lifting this object from here to here. So the force is mg and the distance we lifted that object to is h. So the potential energy is mgh. But when we look at planets or stars, and they have a big mass, and when we look at distances that are not that small, like the one we use for mgh, we can't use a constant g because the g is changing at every level. So the gravitational potential energy we can give by, so small m times, instead of g, we are going to write gm over r squared. And then r, which is the distance from the center of the planet to the mass. So we will find out this is going to be the gmm over r. So that's the potential energy EU. But there's something about the sign, because here we are considering the potential energy on Earth's surface is zero. So we are doing a work to bring the object to a height h. So it's mgh. We have done some work. But in this case, because of planetary scales, we are not going to look at the potential energy zero here or here. What we're going to do is we're going to consider potential energy at infinity as zero. So infinity is far away from here. So we define potential energy as a work done to bring an object from infinity to a point which is r from the center of the planet. So we're bringing an object from here to here. But interestingly, we don't have to do any work to bring an object from infinity to here because the gravity is going to do the job. And because of that, because gravity is doing the job, we are not doing the job, that's going to be minus. So we will put a minus value at the front of this thing. So U is equal to minus U EM minus GM M over R. So M is the mass, capital M is the mass of the planet, small m is the mass of the object, and R is the radius. So that's the equation for gravitational potential energy. So the next one is the gravitational kinetic energy. And now we're going to write the same formula again, which is the centripetal force is provided by the gravitational force. So M v squared over r, because v squared over r is the acceleration, is equal to gmm over r squared. Gmm over r squared. So kinetic energy is given by half mv squared. So from here, if we want to change the first part to half mv squared, half mv squared. So what we are doing, we are multiplying by half and multiplying by r. So we do the same thing for the second part. So we multiply by half and r. So this will become 2r. 2r. So the kinetic energy is given by gmm over 2r. So the potential energy is minus gmm over r, and the kinetic energy is gmm over 2r. So what is the relationship we get from here? We get here that k is actually minus u by 2. Minus u by 2. That's the relationship between kinetic energy and the potential energy. So what's the total energy then? Total energy is equal to the potential energy plus the kinetic energy. So we are going to have potential energy which is minus gmm over r plus gmm over 2r. So what do we get? Minus gmm over 2r. So that's quite interesting, right? The total energy is given by minus gmm over 2r, and the potential energy is given by minus gmm over r. So we are getting an equation that total energy is equal to potential energy divided by 2. That's quite interesting, because does it mean the total energy is less than the potential energy? No, because it's a minus value. So if we have u minus 10, we will have the total energy minus 5. But minus 5 is bigger than minus 10. So because we use the minus values, if the value is less, that means the energy is more than u. So we found the equations for the gravitational potential energy and kinetic energy, and also for the total energy. We always know that the total energy is minus here. What does that mean? If it is minus, that means that object is bound to this planet. So if we want to free this object from the planet, we have to get rid of that minus energy. That is a kind of a binding energy, so that we can free it. So if we have, say, minus 20, if we supply an energy more than 20, that means we can set that free. So if it is minus 8, and if we supply energy 8, that means it will become 0, and it's no longer bound to that planet. So we're going to use the law of conservation of energy, because when we move this object to infinity, the potential energy is 0. And when we move this object to infinity, that planet has no influence on the. So, what is escape velocity? The velocity that we need to provide to this object to free this object from the gravitational attraction. So we have to give this velocity that will provide the kinetic energy to bring the total energy to zero. So if it is more than zero, it will still go to infinity, but it will have some kinetic energy. So what we want is we want the minimum energy that's required to get this object to infinity. So that means when we go to infinity, it will have no kinetic energy because we have given all the kinetic energy, provide the potential energy needed for the object to come to infinity. So let's write down what we have for ui, ki, and uf and kf. So ui is the gravitational energy at radius r, which we found out that is minus gm over r. And ki is obviously half mv squared. And uf is equal to minus gm over infinity. And kf is equal to half m v squared. So let's write the equation using the law of conservation, which is ui plus ki is equal to uf plus kf. So now we substitute all the values that we had before. So for ui, so minus gm over r plus half mv e squared. V is the escape velocity is equal to uf is equal to minus gm over infinity plus kf is equal to half mbf squared. So what we know about this infinity, this when you divide a number by infinity, it's going to be 0. And vf is because all the kinetic energy has been used to provide the potential energy that's needed to bring the object to infinity. So Vf is 0. So we can write that half mv squared is equal to gmm over r. So m and m will cancel each other. So we get ve is equal to square root of 2gm over r. It's quite interesting one. Do you know why? The orbital velocity is equal to square root of gm over r. That means ve is equal to root 2 v. So if we multiply the orbital velocity by root 2, we get the escape velocity. So they're both very useful equations. So this is a summary of that what we have discussed so far. The universal gravitational force is equal to this one F is equal to gm over r squared, and then gravitational field strength we found gm over r squared, and the orbital velocity is equal to square root of gm over r, and we got the equation for t squared, and also we got the ratio t squared over r cubed as a constant, which is same as what Kepler proposed in his third law, which is t squared over r cubed is a constant for different satellites orbiting at different radius around a planet. And then we got an equation for the gravitational potential, which is minus, and then we also have an equation for the kinetic energy and the total energy, and also we found an equation for escape velocity.